actualmente como investigador del Departamento de Fisiología y como subdirector de la Escuela de Graduados de nuestra universidad. Su área de investigación se desarrolla primariamente en el estudio de las vías de transducción de señales que derivan posteriormente en cómo estos sistemas interaccionan con canales iónicos y sus proyecciones para el diseño de fármacos. El doctor Guzmán es bioquímico de la Universidad de Concepción, posteriormente obtiene el grado de doctor en la misma universidad para unirse de manera posterior también al grupo del doctor Luis Aguayo como investigador postdoctoral, donde participa en la determinación de los aspectos moleculares de la regulación del receptor de glicina por proteína G. En paralelo, se une a la planta docente del departamento, estableciendo un grupo de investigación que está actualmente enfocado en el diseño de moléculas pequeñas que inhiben la potenciación del receptor de glicina por etanol a través de modelos bioinformáticos in vivo e in vitro, y en el desarrollo de drogas, nanocarriers y las interacciones que desarrollan su funcionalidad en los sistemas biológicos. En este contexto, ha participado como investigador responsable en proyectos FONDESIT de iniciación, FONDESIT regular, además de proyectos FONDEF-IDEA. Fue director del programa de doctorado de la Facultad de Ciencias Biológicas entre los años 2012 y 2015 y actualmente es director regional de la Sociedad Chilena de Farmacología, SOFARCHI, y su productividad científica incluye una amplia variedad de artículos científicos en diversas revistas especializadas. Entonces dejamos con nosotros ahora al doctor Leonardo Guzmán.
Bueno, muchas gracias por la invitación, Carola, Magdalena. Siempre es un honor presentar ante una audiencia local de regiones y además con invitados internacionales. I want to change now into English. What I'm going to talk about today, that is a parallel project. It's true that the project that I have found that is a FONDESIT project, is more in relation with drug design and small molecules based in bioinformatics and everything. So, but there is another project that is nanotransporters and dendrímeros that we started to develop in parallel to the other one, and this is mostly the work of one of my PhD students, that is Felipe Vidal, and Pilar Vázquez, and all the other student staff in the lab. So, as an introduction, I have to say that there are a lot of challenges in relation to pharmacology, and of course to neuropharmacology. One of the main issues here in those challenges are specificity of drugs, bioavailability of drugs, solubility, of course the blood-brain barrier or choroid plexus barrier, and the intracellular targets that the drug needs to bind. So for trying to solve all those issues, it has been developing the drug delivery system. That there are several drug delivery systems, from a micro delivery system, micro transporter or or transporter from in the size of micrometers, or transporter in the range of nanometers. So we started to collaborate with a chemistry group that did a lot of work with nanotransporter. That's the reason why we study nanotransporter. And this is one of the nanotransporter that we have nowadays in the pharmacology world or in the chemistry world. That is the PAM and the dendrimer. That is basically a simplified polymer from a protein, or is a protein-like polymer because of this bind here. You know, that is pretty similar to the binding of amino acid in a protein. The PAM dendrimers contains a core that is like this, and several other generations that grows from this core, this central core. And there are many characteristics that are very important from PAM and dendrimers. One of them are the generations. This is the 0 generation. This is the generation 1, generation 2. This is the generation 3 here. But one dendrimer can have 4 generations, 5 generations, or whatever. So it's all a matter of size and molecular weight. The other thing is the dendrimers contains what we can call a surface or a terminal groups here. That it's a free amino, you know, and there are a lot of aminos there in the surface or terminal aminos. The other thing is the spaces inside the dendrimer, and those spaces here or here or here, and those spaces can be used to load the drugs, the small molecules or things like that. Here we can load a molecule more or less similar to 1 or no, to 2 or 3 amino acids. You know, so we are talking about of molecules around the 300 of molecular weight, 300 or between 300 or 600 of molecular weight. Okay, this is easily modified. We can easily modify the surface, binding several other chemical groups, for example, amino acids or peptides or nucleic acid of several kinds. The main use in pharmacology is to increase the solubility of certain drugs that are not very easily soluble in water. Dendrimers are a well-defined structure and size. That this is a very good point also. It is highly soluble in water and interact with molecules, even with larger molecules, like in this here. This is what I was explaining. The drugs can be inside the dendrimer, or can be attached in the surface, or the dendrimer can bind to molecular bigger than a drug, a typical drug. So the story starts with a collaboration that I have with those chemist guys, Joel Alderete and Veronica Jimenez, and we started to collaborate in the drug design, small molecule design, bioinformatics, and things like that. And in one of those meetings, they started to talk between them. A thing in relation with dendrimers, with PAM and dendrimers and things like that. So I asked, what is that thing of the dendrimer? Dendrimer is a polymer that we are working in, and it's very interesting because this and this. What is the uses? What are the uses of a dendrimer? And they explained they use it for pharma, for loading drugs and solubility of drugs and everything. So can I obtain some of those dendrimers? Yes. I can't wait. And we started to create an entire project. And Felipe Vidal is really the great motor to obtain all those results that I'm going to show you. But also I come from a group in neurobiology. So the thing that I started to get interested in the uses of dendrimers are always in relation with neuro things, you know, neuropharmacology or synaptic activity and everything. So the first thing that we discovered some years ago is there wasn't many details or detailed studies in relation with dendrimers and neurons, and not many studies in dendrimers and brain-blood barrier or synaptic activity. All the things that are in relation with neurons or neural activity and dendrimers were not very explored. So we started to go that way, always taking into account that for any drug that needs to get into the central nervous system, the drug needs to cross the blood-brain barrier. That is a physiological barrier. In any case, there are some studies in relation of biodistribution of dendrimers in a rat. There are some dendrimers that it seems to get affinity for central nervous system, for the brain here. But there are many details in relation with that. This is the work of Albertazzi, that is one of the scientific groups that goes more deep in the investigation before us. Before we appear in the scientific museum studying dendrimers, Albertazzi did some experiment in relation with dendrimers and interaction with neurons. But one thing that take our attention is, in any case, there weren't many details in relation with association of dendrimers with neurons, and one thing that it made me wonder many things is the times they use in order to test the interaction of dendrimers with cellular structure. I don't know if you notice here the time. This is 1 hour. After 1 hour of incubation of the dendrimer, that in red, with the cells, there is a neuron. And this is another experiment with after 4 hours of incubation. 4 hours of incubation. For in a molecular time, or for a time lapse in the molecular range, 1 hour is a lot. I mean, it's an eternity, and 4 hours also, and 24 hours is many things happening. So we try to go again to this kind of experiment, but trying to do it in a more detailed way. This is another typical experiment. What's happening with PAMAM concentrations of several generations. What's happening with cell viability in one kind of neuron. So our general objective was to perform biological studies of PAM and dendrimer interaction with neurons, but in a more detailed way, or with the techniques that we have here. Of course, CMA, that is a very good facility in microscopy, with the chemists collaborating with us and everything. So one specific objective is the neuron to study the neuronal internalization of permanent primers and specific effects of synaptic effects of dendrimers in neurons. So those are the dendrimers that we wanted to study. This is the first one, that is the G4. The G4 is just a PAM dendrimer of 4th generation, with the amines there in red. And all of them, we bind a PIC fluorescent dye. So all of them, we can track all of them in cytoisochemistry or immunohistochemistry or immunocytochemistry. This is the other one that another dendrimer that contains the 50% of the terminal amines bind it with polyethylene glycol. There is a big polymer also. This is another one that contains the 25% of the terminal minus associated with acrylate. This is another one that is very interesting because it contains folate in the surface, in the 25% of the A minus. And why is so important? Because folate, there were some studies that demonstrate that folate could be a molecule that can help to other molecules or other polymers to cross the blood-brain barrier. So we were very interested in see what's happened with this dendrimer. But the first thing we did is try to repeat the experiment of Albertazzi with all these polymers, dendrimers I show. In red, there, you can see the polymers, the dendrimers. This is hippocampal neurons. This is after 30 minutes of incubation with the dendrimer, and the G4 is associated with neurons, and the dendrimer with folate, the PFO, is also associated with neurons after 30 minutes. But as you can see, nothing happened with the other dendrimers, PEG or AC, that is acrylate. We repeat this experiment after 30 minutes, 1 hour, 2 hours, and nothing. We never see association of these dendrimers with neurons, but and we always see an association of G4 and PFO with the neurons. But as I said, I wanted, and it was an order of mine, I want the detailed studies of internalization. So Felipe did an experiment starting with an incubation of 30 minutes, and after that, watching the dendrimer from the neural culture, and started to track the fluorescence at immediately after the watching step, after 2.5 hours, and after 5 hours. Yeah, but without adding more dendrimer. So we did this. These were the results with the G4. Sorry, this is G4. We start to see here at 0 time the association of the dendrimer more in the surface or in the periphery of the neurons. After 2.5 hours, two things happened. One thing is that they started to form some kind of bigger points. I don't know how to say it, bigger things, you know, in red. And after 5 hours, those points, how to say it in English, accumulos around dots, right? Started to go in several to several directions inside of the neurons here. Something very similar happened with the PFO dendrimer. You can see here in the periphery, and after that here what it seems like a cytoplasm of the neurons. But we wanted to quantify this, and we created, I don't know if we created, but we decided to quantify all of this, taking this rectangle there, or here, or there, and quantifying in several positions and in several neurons, and quantifying the fluorescence, the green fluorescence. And we obtained this graph from the membrane to the inside of the neuron, with the 3 times of after incubation. This is with so at 0 time after incubation, all the green was more in relation with the peripheria or the membrane. We put their membrane, but it's the peripheria of the neuron. And after 5 hours, the main of the green fluorescence was more inside. And the same, more or less the same thing happened with the PFO dendrimer. So next step was to say, okay, it seems that dendrimers are internalized by neurons, but there is a kinetic or kind of a kinetics. It seems that vesicles have something to do with that because of the shape that the green fluorescence take after 2.5 hours. So we decided to use some inhibitors of several kind of endocytosis, and we use cipro. I forget the name.
Chlorpromazine.
Chlorpromazine. We use chlorpromazine here to study the internalization of G4 and Philippine. Chlorpromazine is more in relation with an endocytosis associated with cluttering endocytosis, and Philippine more in relation with caveola endocytosis. That are two of the main kind of endocytosis, or at least 2 kinds. And we could see here that the G4 dendrimer is more, the internalization of G4 is more inhibited when using chlorpromazine than when we use Philippine. This was very interesting because for PFO dendrimer, we inhibited also with chlorpromazine and with Philippine, with both inhibitors. So we obtained a big conclusion here that actually the dendrimers were internalized by it could be one specific or not so specific endocytosis mechanism in relation with cluttering or caveola. So next step was to try to determine where the intracellular trafficking that these dendrimers had, and we studied the cluttering associated mark of the dendrimer after the internalization, the caveolin and RAP5. RAP5 is a protein that is associated with vesicles inside the cytoplasm. For the G4 dendrimer, we could see association with cluttering, a little with caveolin, and of course with RAP5 that demonstrate that G4 dendrimer after internalization is after internalization follows a traffic step that is associated with some protein that are characteristic for this kind of trafficking, intracellular trafficking. For the PFO, it was something similar, but the association with cluttering was 0.4, with caveolin was 0.5, and with RAP5 was 0.4 again. So we could demonstrate that first, just the G4 and the PFO dendrimer can be internalized by an endocytosis mechanism, but the modification with acrylate or polyethylene glycol inhibits its possibility to be internalized in neurons.
it seems that these two kind of dendrimers are associated more or less to mechanisms of endocytosis associated with clustering or cabling, and they both are associated after a while with early endosome, that is, that we can use the RAP5 marker for that. So the next step was, okay, we said, okay, we could describe what more or less what is the mechanism of internalization of common dendrimers, but what's happened with toxicity. There were several reports of toxicity of dendrimers in neurons, but we wanted to be more in detail with that. We used these two kind of, these three kind of dendrimers, the G4, the BFO25, or the polyethylene modified. First thing again was to measure the cytotoxicity of neurons. G4 is more or less toxic because when we use 1 micromolar, we can see a 50% of toxicity. And when we use 10 micromolar or 100 micromolar, we could see a very high levels of toxicity. But in any case, okay, we can see here toxicity, but those concentrations are not very pharmacologically relevant. But there are data that demonstrate that D4 could be toxic in some cases. What was interesting was the effect of PFO 25 that reduces the toxicity, the binding of folate to the surface of the dendrimer, reduce the toxicity, as you can see here, and same thing happened with the dendrimer modified with polyethylene glycol. But here I have to mention that that's a good thing to work in a very interesting, how to say, interesting and interactive group of young scientific, because when we were studying this result, I remember that Fernando Segovia here with other colleagues several years ago started to develop a technique where they introduced in the patch clamp pipette, they introduced the A beta peptide and started to see what's happening with the capacitive current. The explanation of this is pretty long and boring, and I don't know if I'm going to explain pretty well. So, but I have to say that if you have a pipette, if you're doing patch clamp and you have the pipette here and the cell here, and you attach the pipette pretty well to the neuron or to the cell, you obtain these currents here, okay? And if you can open this little piece of membrane and take in electrical contact the solution here with the cytoplasm, you will obtain a current like this, okay? And we did this, but without applying any force to remove this little piece of membrane, any force but the introduction here of G4 with the PFO or the polyethylene glycol modified panel. And with the only one that we have a response like this was with the G4. So this register here demonstrates that for some reason G4 did a hole or several holes, or we cannot do the very detailed interpretation of this, but G4 generates electrical connection between the internal solution here and the cytoplasm of the cell here. It was time dependent because in the first 4 or 5 minutes, nothing happened, but after minute 10, or we started to see that in some cases the patch opens, after 20 minutes the patch was clearly open, and it launches after 30 minutes. And with the other Dendrimers, nothing happened. So if the G4 or the Dendrimers are doing holes in the membranes, so the next question was, well, what's happening with the calcium? With the calcium metabolism, cellular metabolism of calcium, or cellular dynamics of calcium. So we measure calcium, and I'm sure you more or less know how to measure calcium, intracellular calcium, that is using a proof that is fluorescent in presence of calcium. After binding of calcium, increase the fluorescence. So we obtain these kind of registers with these Dendrimers. The highest level of fluorescence here was with the G4 here. This is the typical register of calcium in neurons. You can see those spikes here that we call it calcium transient, and it's pretty normal. But this thing was very, very rare, very strange. So Felipe insists in trying to analyze the area under the curve here, but well, we obtained this a lot of the area under the curve was very, very, very high, and the frequency was very low. What is strange also, but it is understandable because the phenomena here is so big that we cannot see any frequency of calcium transients.
Did you apply directly to the cell or to the bath?
Yeah, in the bath, in the extracellular solution, right? Yeah. This phenomenon of the G4 Dendrimer was extracellular calcium dependent, because if we use G4 but without calcium, we couldn't see anything. So G4, two things. G4 seems to do holes in the membrane and to alter in a very drastic way the calcium dynamics in neurons. So we decided to check what's happened with the delivery of neurotransmitter, or saying it in a better way, and the dynamics of vesicles. And we used another proof, that is FM143, and that fluoresce when inside the cell or the cytoplasm, but when the vesicle take contact with the extracellular solution, it decreases the fluorescence. So, for example, this is the signal of the vesicles in a control condition, or in presence of these two Dendrimers, but in presence of the G4, the vesicles start to the dynamic was very faster, faster than in relation to control. So it seems that vesicles go very rapidly to the membrane and started to flow very, very, very fast. We calculate some decay rate constant. So of course, next question in a neurophysiology laboratory was what's happened with synaptic transmission. We did these registers. It's a lot of people. Felipe and other students did this experiment in a control condition. We could register this. That is a typical register of synaptic activity. We used these two Dendrimers, and we couldn't see any big difference in frequency of synaptic events, But when we use the G4 dendrimer, we could detect a very high increase in frequency of synaptic events. The same thing we could check with the amplitude of the events. So basically, what we could see is that PFO or polyethylene glycol modified dendrimers or the G4 dendrimers can maintain a normal physiological condition for the synapse. But the G4, so what is it? So, sorry. The G4 introduced a very drastic change. It seems that G4 is doing holes in the membrane that alter very drastically the dynamic of calcium, that increase the mobilization or the vesicles mobilization to the membrane, and increase the frequency of synaptic events. So one of the things that are important to check any time that you have to use a G4 dendrimer is what are you using G4 and the toxic effects that the G4 could have in neurons. Another very open questions are in relation with the histological distribution of dendrimers. This is some experiment that Felipe obtained in Germany in relation with G4 and PFO dendrimers after injection to rats, intravenous, yeah, right, in the intravenosa. Intravenosa is in English intravenous, right? Okay. Intravenous injection of dendrimers here in red, and we obtained some interesting images that demonstrate that G4, for some reason, has the ability to associate with core reflexes, and the G4 also, but a lot less. However, in other brain areas like dentate gyrus, we cannot see a lot of signal of dendrimer for some reason. Or in the cortex, there are some points there or dots there, but not too many in any case. In liver, we obtain a very high level of intensity of signal of the dendrimer in liver here after half an hour after injection, that decrease after 1 hour and after 4 hours here. PFO behaves a little different. Here we have the image after half an hour, 1 hour, and after 4 hours. It seems that PFO reached a very high level in liver after 1 hour, but after that it is very fast. The clearance is very fast. This is kidney, several structure of kidney. We obtain a lot of signal in kidney, so there are very interesting things to study here in kidney, but for kidney scientific interested guys, so maybe not for us, but so there are other questions in relation with biodistribution. In general, conclusions here we have. Surface properties of common dendrimers plays a key role in their interaction with neurons. Seems that positive charges in the surface are very in relation with internalization mechanisms. Those modification of the chemical surface activate internalization mechanisms that could be different, a little different, depending on what kind of chemical modification we apply to the dendrimer. There are neurotoxic effects and synaptic activity alterations in the G4 when we use the G4 dendrimer, that is the basic fourth generation dendrimer. Folate modified dendrimers are not very easily uptaken by the central nervous system tissue. This is not very in line with previous observations of other scientific groups that seems to think that folate, for some reason, could be a very good tool to direct the drugs or polymers or whatever to the central nervous system. In our hands, folate is not so easy to demonstrate that. So, but we are trying to investigate to do some research in that. This is the group on last year. This is Felipe Vidal, the main responsible for all these results. Pilar Vasquez, also very talented student with Francisca Cayuman and Jennifer, and this is Josefa and Andres, and this is me, and other students and technical staff. This is Jorge Alderete, from the chemistry side of the dendrimers, and this is Veronica Jimenez from the bioinformatics, and our German connection, that is Christoph from field that is supposed to be coming on summer for the summer course. So now if you have any spondylosis, the title of the spondylosis is small molecules and G proteins, and nothing relation with that. That's always we can use the money for other things.
Tenemos tiempo para algunas preguntas. ¿Hay preguntas? ¿Sí?
Leo, did you see some change in the behavior of the animal when you applied the G4 by a injection?
Yeah.
Something?
The first thing that we see is that they die.
Okay.
Because and that was sad. Yeah. We're going to the hell of rats or mice. And we did a mistake in the concentration. After that, we discovered that we apply a lot more. But in using the right concentration or the right doses of the dendrimer, you cannot see any behavioral
Something like a
change.
desensitization or...
No, nothing at all. No, it's very safe. It's very safe in those terms.
Jorge.
Leo, the experiment with calcium and solution without calcium appears to be very interesting because one possibility is that the G4 maybe make a pore in the plasma membrane, right?
Yeah.
But have you seen, or do you think that this G4 can modulate, for example, some calcium channel and make to open?
Yeah.
Stable?
Yeah. We did, or Felipe did some experiment with some calcium channel blockers, and the effect of G4 at least in calcium dynamics is not dependent on the activity of calcium channels. I didn't want to show those results. It was too long.
¿Alguien más? Sí.
Only one question. Can you mix this dendrimer mixed before with the folate? Because before is very toxic, right? But if you use a very low amount in order to just
Yeah,
to
yeah.
get the child to open the neurons, right? And then with the folate, because it's not very good, maybe you can do a very good dendrite.
Yeah. what is I think what is better to do is to modify the G4 with less folate. We use 25%. That is 25% is from 32 is 8 molecules of folate in each molecule of G4 dendrimer. So, but chemistry guys, the chemistry guys can do a lot of proportions. So maybe it's a good idea to reduce the amount of folate more than mixed. I think the problem with the G4 is not so toxic. But, right. The G4 is not so toxic, but if anybody comes to me and say that has a version of G4 or something that is a lot concentrated in certain brain areas, I would say, oh, take care with that, because we demonstrate that there are some synaptic effects that are not very good, you know, so that could be a problem with that. So maybe the good way to do it is try to modify it in order to go directly to certain neuronal spaces. And we have a project that we're trying to investigate what's happened if we add some peptides to the surface of the dendrimers in order to direct the binding of the dendrimer to synaptic structures in order to deliver the drugs there in a more specific way.
Yeah, that's what I mean. So, I want to say modify, not mix, modify the before, not with the folates, or in order that we will have a really nice
Yeah, but
dendrimer to do.
in our hands, folate is maybe not a very good molecule or modification to cross the brain-blood barrier. It's not very good. So it's a good idea to modify the dendrimers, but we have to test some other peptides or molecules in order to direct the delivery of the drug to certain brain areas or areas in the body, whatever you want.
Le damos